Welcome back. I'm the Tutor Wizard. Please subscribe right here and you will get notifications for this series and a bunch more series talking about all kinds of different mathematical topics. What we're going to do this time is the Tower of Hanoi. We're going to discuss an ancient mathematical game, or a mathematical game. I have to put math in there. It's a puzzle. It was a logical game with a couple rules, and we want to know basically how to play the game. What we're going to do is first play it, and then we're going to start analyzing, and then mathematically it's going to get all the way down the rabbit hole. Well, halfway probably down. What's halfway to infinity? Still, you got pretty deep. What we're going to do is we're going to start asking questions about, can you solve this using the rules? That's step one. Here's a game. You let a bunch of kids play. Can you solve it? Then you say yes, and you're like, haha, I did it. Then what we're going to do is we're going to say mathematically we want to optimize it and do it the fastest way we can. So then we're going to ask the question, if you can find a solution, which we can, what's the shortest solution, or what's the fastest solution? And what we mean in this problem, it's dependent on the puzzle that you're using, but in this puzzle it's going to mean what's the minimum number of moves that it took me to move these counters to find the correct solution. So what are we going to do with this? Let's analyze what the puzzle is doing. What the Tower of Hanoi is we have a bunch of discs of different radii, or they're smaller discs to larger discs at the bottom. This is the initial state, or the starting point of the game. What the game wants, or here's the puzzle. What we're going to do with the puzzle in a second. In my hand, I'm going to play it for a few rings, including up to this one, and then 5. Trust me, you don't want to watch me do 5. Now let's do 7. Let's do 15. Let's do 27. Yeah, you don't want to see me do that. You'll see in a second where I like the theory of not actually trying to do this. There's one in Tibet, I believe, in a monastery. I don't know if it's in Tibet, but there is a monastery that has one which is 64 rings. We're going to see that, yeah, don't go there and be like, I'm going to crush out the 64 ring. No, you're not. You'll be old. You'll be really old. What's the rules? The rules are I have to take these discs, or n discs in general, but if I have 4, I need to take these 4 discs and move them so that they are over here to the left peg. I'm allowed to do this moving 1 ring at a time. Each ring has to go to another one of the 3 pegs. We can label these pegs A, B, C. And you can do all kinds of clever patterns, and we're going to find a pattern for which rings or where they went, and you can start doing all kinds of clever mathematical analysis for this. But again, all I want to do is move these rings so that they look identically the same tower over here. The 2 rules are, in each move, I can only move 1 ring, and it has to go on to any one of the pegs. You can put it anywhere you want, but the other rule is you can never put a larger disc on top of a smaller disc. What I mean by that is, here's a bad move. For students, they're like, well, could I do this? Or especially the younger ones, they always try to break your rules. It's immediately you give them a rule, like, well, what, they want to push the boundaries of the rule. Could I slightly? No, I mean, you can't do that. You can't put a bigger one. Well, what if he's just really close to the same size? No. If he's big, so they try to push. So what do I mean by this? You can't do this. I'm going to use different colors. We'll use, this is a big ring, and this is a smaller ring. This is bad. You're not allowed to do this. What's a good one? What's good is you're allowed to do, now I get to see how I have to juggle the pens in class in real time. This is a good move. In any move, you're allowed to move them, and they can go onto any peg you want, but you can't ever do this. You're only allowed to do this scenario, and it doesn't matter how much bigger they are. You can have a really teeny tiny one, I don't care, but they have to go biggest ones on the bottom always. Is essentially the rule. Let's get into what that actually looks like for the puzzle. What we're going to do is, I'm not going to do 7, blah, blah, blah. Let's use the same colors, pink, orange, yellow, you're out, sorry Mabel, yellow's out, purple, green. So we'll start with those ones. Now I've got 4, just like the picture. What we're going to do is move them to this peg, and I want the green one on the bottom. And you're like, no. So what you want to do also is rush into the game, and I give you this game and you just want to start playing the 4. What I'm cleverly going to do is try to find a pattern. We're going to start and find the pattern immediately. I'm going to play the game with 1 instead of 4. I need it to go here, and I'm allowed to move 1 in one spot, and oh, easy, 1. I'm going to start keeping track of that. For 1 ring, it took me 1 move to solve. I don't need that. Now let's do 2. What comes after 1? 2. Now I have 2 rings. I haven't moved to here, but I can't do this now, because if I would try to do that, oh, that's not the solution. That's the solution upside down. Yeah. So what I'm going to do is, luckily I have 3 pegs, so I can move the little one here first. And notice that was solving it on the second peg. And now I'm going to move this one big guy once, and then I'm going to move the little one again. So what I did for 2 rings now, one and many still in our language, singular, plural. One thing, more than one thing. 2 rings. What did we have? We had 3 moves to solve. Where do you think I'm going with this? 3 rings. And then guess what it is? Ariana Grande, 7 rings. The original problem was that I have is 7 rings. But we're not, we won't go all the way to 7 rings. You can do 7 rings and listen to the song while you're trying to solve it. What's 3 rings going to be? 4 short of 7 rings. Yes, you're correct. But we're going to add a purple on there. And then now let's try to, whoa, where are you going? Go in row. Now what I have to do is I have to move the purple one to the bottom here. Or he has to be on the bottom. So I've already solved this a bunch of times. Well, what I'm cleverly going to do is put the blue one. I'm showing you how to systematically solve these as we go. I'm going to put the blue one there. Now I have an open peg and I can put the middle one there. Now I want this one to be here, but I can't do that. That would be bad because he's on. So what we're going to do instead is now I can cleverly do, again, notice this time I solved the 2 ring puzzle on the middle square. Now I move 1 move to move the biggest ring of the 3rd ring in this case. Then I can't go that way, so I'm going to move him off so he's little, and then there we go, the 3 puzzle. How many moves was that again? Wizard easy. So now let's do it again. Now let's count how many moves it takes me. 1, 2, 3 moves. 1 move. 4, 5, 6, 7 moves. 7 rings. No, 7 moves for 3 rings. 1 more time, 4 rings. How many moves are we going to get? Any guesses? What's the next number in the sequence? This time I have to actually do it because I need to put the word on there. Now 4. Now I can't remember already. I want to move the green one to here, and he's on the bottom. So what I want is this one open eventually whenever I move stuff, and everybody to be on here. So what I'm really actually going to do is I'm going to solve the 3 ring puzzle, but I'm going to move it to this peg. So I'm going to solve the 3 ring puzzle right now, but on the middle peg. 1, 2, 3. Now I'm going to move this 1 ring over. 1. Now so I'm going to have to do that again, unfortunately. This is why you want to see me do 5, want to see 7? No, 64. Yeah, good luck. Now what I have to do is put it here. And it was an odd one. So I'm going to do this, then this, then this. Move him there. Then move him off. Then on. We get the 4 ring. How many was that? I'm going to start cheating already and seeing what the pattern we want to start noticing. That was 7 moves plus 1 move for the green one plus 7 moves to solve the 3 ring puzzle again after. So again, what we're doing is I solve the 3 ring puzzle to put it in the middle. Then I move the 4th ring over 1 move. Then I solve the 3 ring puzzle to put it on the last peg. So what is that? 2 times 7 plus 1, which is 15, is the next number in the sequence. But now I want to start looking at a pattern in the minimum number of moves. This is the minimum number of moves for the first 4 Tower of Hanoi puzzles, where I use 4 rings, 3 rings, 2 rings, or 1 ring. Once I start noticing this pattern, I want to flesh that out and find a nice formula for that for every n and see how long it would take to solve the 64 ring Tower of Hanoi, possibly if it took me 1 second per move, or how many moves is it going to take. First, if I can calculate how many moves it takes, and then I can say how many seconds or how many units of time does it take per move, then you can say that thing would take this amount of time. Extremely useful in computer science. I think I have a pattern. Let's check it one more time. Here explicitly is the solution, magically. What they're doing in those pictures is they're showing you how to solve and go from this state to the end state, which is going to be this flipped around. When they do that, what they're trying to do is analyze, and they're trying to find a pattern of who I've moved and how many moves it took to move who we moved. So what they're doing is in these pictures is they're keeping track of who gets moved where on the pegs, and then how many or the minimum number of moves I would have to do in each step to get this. For the 4, well, let's do the 3 case instead of the 4 case. How do we do that? We get rid of the green one. We'll do the 3 Tower of Hanoi. For that one, quickly what I'm saying is I took the 2 pegs, these 2 guys, and moved them to the center. So to solve the moves for 3, I take these 2 guys and I ignore that ring, and now what I'm technically doing is I was solving the 2-ring puzzle. And how many moves does it take to do the 2-ring puzzle? It takes, for the 2-ring puzzle, it takes 3 moves. And I do that to move him there. So then that means I've done 3 moves to move that minimum, this smaller tower over here. Then I move this guy here. That's 1 move. Then once I've moved the purple there, where's the purple? Once I've checked, so in this one, the 2-ring moves, what I've done is that and that. Then we have that state is what the picture's saying. Once I do that, and they describe that in each move one at a time, now I can move him over, so I get the purple over here. And that's, I just moved 1 move. Then I have these 2 rings, and they have to go here, so I'm going to solve the 2-ring puzzle again. He's going to go here, and he's going to go there, and he's going to go on, and we're going to get, magically, that I get it solved over here. In the last step, to move that to there, again, what do I get? Rid of these markers, and I have 3 more moves. And that is telling me, and then we're trying to find a pattern, so algebraically what we're noticing now is if I want to know how many moves, we're going to call it T for the 3-ring puzzle. We're going to call Tn the number of moves it took to solve the Tower of Hanoi. T3 takes, well, this was a T2 solution. This was a T2 solution, and there's 2 of them. And so we noticed that that was 2 times the number of moves it took to solve the 2 tower plus 1 move to move that ring over. And so what we're noticing is we solved the 2 puzzle, we moved the 3rd ring once, then we solved the 2 puzzle again. For the 4 puzzle, we have the 4 on the bottom. You saw me fumble through it a couple times, or I don't know how he edited it, but you saw me get it eventually. If first you don't succeed, try again. You think I don't get it right every time? Yeah, I prepped it and I did sitting at the table, it worked great. And then I get it in front of a camera, it's like, 3 tries. Once you get it, I notice a pattern. When I did the 4, I moved the 3 solution, this one, then I moved the 4, then I moved the 3 to get on top of it. So that was doing, let's do that one more time. To do the 4 rings, that was T4 was what? Well, I moved the 3 rings over, and then I moved the 4th ring, 1 move, then I moved the number of moves it would take to do the 3 moves again. So that is what? 2 times T3 plus 1 is T4. And we start suspecting we have a pattern. We're now going to say Tn is 2 times Tn minus 1 plus 1. And now we've found, looking at that pattern and analyzing how the game goes and looking at the minimum number of moves, calling Tn the minimum number of moves, we now have what we call a first order non-homogeneous recursion relation for the minimum number of moves in Tn to be dependent on 2 times the minimum number of moves for the n minus 1 ring puzzle plus 1 move to move that last peg. Now what we're going to do is we're going to find a closed form for this so that we can calculate. I'll give you 2 ways of doing this, and then we're going to prove it by mathematical induction, just because how do you know it works for every n larger than or equal to 1? We're going to prove it today. If you don't like that, we're going to do separate videos on what recursion relations are, including linear and nonlinear and homogeneous and non-homogeneous. We'll go through all of that, watch that video, and then if you want to know about mathematical induction, there is definitely going to be a video on mathematical induction as well, at least one, so watch those. That's what I'm about to do now. What we have is what we think is a recursion relations or a recurrence relation, depending on, this is, remember, the minimum moves to solve the Tower of Hanoi problem. What is that problem? To recap, you want to move all the rings on 1 peg to the from the right peg to the left peg only using 2 rules. You can only move 1 ring in each move, and you can't put larger rings on top of smaller rings. Doing that, we found out that analyzing this for several cases, we found that we're pretty sure that the number of moves to do the nth ring depends on doing the n-1 ring problem twice and then moving the big ring. First you do the n-1 problem to move everybody off of it, then you move the ring onto the peg, then you do the n-1 ring problem to put it back onto the tower, and then you've got the new tower. So this is what the recursion relation we have. We now want to find a closed form for that. What does that mean? Closed form. This one means that if I want to know what T1 is 1. Then this will be for n greater than or equal to 2. For T2, this is equal to what? Well, 2 times 1 plus 1, which is 3. T3 equals, so if I want to know what T4 is, I have to compute all the way up because I have to use it. See, I'm using this one in the next one. T3 is 2 times T2 plus 1, which is 2 times 3 plus 1. I have to use the previous, which gives me the 7 that we just computed. Then I want T4. T4 is 2 times T3 plus 1, which is 2 times 7 plus 1, which is 15. Not comp prime. 3 times 5. T5 is equal to 2 times T4 plus 1, which is 2 times 15 plus 1, which is 31. T6 is 2 times 31 plus 1, which is 63, not prime. And T7 is equal to 2 times 63 plus 1, which is 127 moves to do Arianic on 7 rings. To do 7 rings is going to take 120. You don't want to watch me do that one. I don't think I've ever actually done it. Somebody do it and be like, I did it. Wizards. That's who does that. This is what we're talking about. We now have a pattern, but if I want to know what T7 is, I have to compute all the way up to T7 to find out that it takes 127 moves to move 7 rings. I want to find what we call a closed form for that, so then I have a way of calculating for whatever 7 is. I just put it in there, I calculate it, and it tells me 127 based on that. How are we going to get that? I'm going to show you 2 ways. Method 1. I just iterate this over and over and over again. What we have to know also is an initial condition. You have to have a starting point. You have to know what the first one is if I'm going to find everybody else. And now what I cleverly do is I just keep putting that in over and over again. First of all, what I see is I can substitute the index. So if I want to know what n is, I want to know what 2n is or something for a formula, sine 2n, or if I have the formula for n, I just put 2n in there. If I want to know what the formula for n is and I want to know what n-1 is, I put that in there. So Tn-1 is going to be 2Tn-2 plus 1. Right? And Tn-2 is going to be 2 times Tn-3 plus 1, and all the way down. Any number I put in there, they're all going to be dependent on, that's just saying they're dependent on 2 of the previous ring move problems plus moving the 1 ring. So I'm just going to keep putting those in there over and over again till I get down to T1, and I know what T1 is. So then we can have a formula for this. This is the ad hoc method of when I first do recursion relations. How do you solve basic ones? You just put them in there and try to find it, and they're like, well, does that actually work? Well, don't worry, it does, because we'll prove it by induction for every n. What is the method now? From this, I'm just going to iterate this. This is 2 times, what's Tn-1? That's 2 times Tn-2 plus 1. Plus 1. I just put in who this guy was. Now clean that up, watch cleverly. Oh. Now I'm going to put, who's that guy? Well, that is 2 to the 2 times, he is 2 times Tn-3 plus 1 times plus 2 plus 1, which is 2 cubed Tn-3 plus 2 squared plus 2 plus 1. Oh, I see a pattern of power, a geometric series coming about. And then this is going to equal ... when we get to the end, 2 to the n minus 2 times 2 times T1 plus 1 plus ... plus 2 plus 1. Don't worry, I've done this before. This is the ad hoc. You're like, I didn't like that. I know. I'm going to give you a systematic way of using theorems to solve all linear, non-homogeneous recursion relations with certain non-homogeneous functions in another video. Right now, what does that give me? Simplify all of this, and what do I get? I really like this, so bring it back to the top. What does that give me now? After I have this, I FOIL everything out. That gives me equals 2 to the n minus 1 times t1 plus 2 to the n minus 2 plus dot 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 plus 2 squared plus 2 plus 1. Who's t1? 1, luckily. So this is equal to 2 to the n minus 1 plus dot 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 plus 2 squared plus 2 plus 1. Tangent. X to the n plus dot 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 plus 1 is equal to x to the n plus 1 minus 1 over x minus 1. Proof. I let this thing be a. Then what's xa? X times a shifts all the powers, so this will be x to the n plus 1 plus x to the n plus 1. Subtract those from each other. What do I get? Oh, no, this one has no. He shifted, he has no constant term anymore. They all go away. Minus, that gives me xa minus a equals x to the n plus 1 minus 1, or a equals x to the n plus 1 minus 1 over x minus 1. You can prove this by induction too, but so look, I just use this to put that in here. Now my base is 2 and I have n minus 1, so it would be n minus 1 plus 1, which would be 2 to the n. 2 minus 1 is 2, so we get, using this clever theorem, a closed form for Mersenne numbers. This says what? Tn is equal to 2 to the n minus 1. This is known as a Mersenne number. If it's prime, it's called a Mersenne prime. If the n is composite, you can't get a Mersenne prime, but not every prime number gives you a Mersenne prime. 11, try 11. 2 to the 11 minus 1 doesn't give you a prime, it's composite. Watch our other videos on Mersenne numbers, and we're going to do all kinds of numbers. All kinds of numbers. Now we have a closed form. If you didn't like that, you're not going to like the heavy machinery I'm about to do now, so skip forward 2 or 3 minutes. Proof 2 of this closed form. Tn 2 times Tn minus 1 plus 1, T1 equals 1, is a non-homogeneous first order recurrence relation with initial condition T1 equals 1. I need a starting point, and then it says you can compute this. Now remember, what that says is recurrence relation is fancy words way of saying it's a list of numbers, and I get each number in the list by knowing previous terms. The Fibonacci sequence, which we're going to do a ton of videos on, is a recurrence relation where the nth Fibonacci number is just flowers add by doing this. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is, start learning about Fibonacci numbers. This is a recurrence relation also. What ours is a Tower of Hanoi recurrence relation. This is second order because I have two, it depends on two guys. First order has nothing to do with Star Wars. It has to do with the fact that it only depends on one of these guys. Well, it has a little bit to do with Star Wars, but there's no wizards in Star Wars. Wizards in Lord of the Rings. Lord of the Rings is better than Star Wars, I'm sorry. Shh. Comment below if you disagree. Too bad, I got the microphone. So that's what this mumbo jumbo means. This guy depends on one of these, It's non-homogeneous. What's that mean? This is there, so it's not 0. If that's not there, then we can call it homogeneous. And then the initial conditions just means we needed a starting point. Fancy ways of saying that. What does that mean? The general solution will be Tn homogeneous plus Tn particular, where Tn homogeneous is the solution to the associated homogeneous solution recurrence relation, and Tn particular is the particular solution to the non-homogeneous recurrence relation. I'll give it in 2 pieces. Here we go. Here's this one and this one. Step 1, how do I do this guy? Homogeneous solution. We assume that t to the n equals r to the n for some positive real number, cleverly. What does that mean then? Well, putting that into the recurrence relation, and then we're going to put that plug into Tn equals 2Tn minus 1. If r to the n equals Tn, then again, what's Tn minus 1? R to the n minus 1. So this gives me r to the n equals 2r to the n minus 1. I get a characteristic polynomial, the same way I do in eigenvalue eigenvector problems, and the same way I do in ODEs and stuff like this. When we're looking for characteristic equations, we do the same guess when we solve second order homogeneous and non-homogeneous ODEs. We make a guess this. The solution is r to the n. Now what are we going to do? This gives me r to the n minus 2, r to the n minus 1 equals 0. I have a polynomial in r. Factor this, r to the n minus 1, r minus 2 equals 0. My characteristic polynomial is r minus 2. The only root of that is r equals 2. So this is a solution to my homogeneous recurrence relation if and only if r is 2. So that tells me my Tn homogeneous is equal to a times 2 to the n. And in these, if you know what we're talking about, and you've seen recurrence relations before, once I find the a, this means that this is the most general solution. We're going to find the coefficient a at the end using the initial conditions after I find a particular solution. So I do step 1, I find this up to the constant. Step 2, I find the particular solution. Then I write it as a linear combination. Then I use the initial conditions to find out what a is. A is 1, 2 to the n minus 1. B is going to be negative 1. Step 2, this is the homogeneous solution. Half I need. The general solution is the linear combination of the homogeneous solution and the particular solution. Same as in ODEs and everything else. Aye, Captain Wizard. Stop talking to yourself in front of the camera. I'll do what I want. 2. Particular solution. Tn particular. How do we find that guy? I don't know, you're telling me, you're doing the videos. Okay, that was rhetorical. Fn. This is non-homogeneous because this is our Fn, is 1, which is actually, this is why I picked danger, is 1 to the n is who that guy is. But what do I have to check in this? Your polynomial can't have roots of your polynomial, the roots of the particular characteristic polynomial. So remember, P of r was r minus 2. And so 1 is not a root of P of r in this case. If it is, we multiply by n, remember. If you know what I'm talking about. If not, be like, finish up so I can see what you get the same thing. It'll be the same thing. So it's not, I have to make this check. Is the root, is this guy a root of your characteristic? If it is, multiply by n to the number of times it appears as multiplicity. Anyways, by that. It's not, so we don't have to worry. That means we're gonna guess Tn particular is going to equal b times 1 to the n. If it was a root here, if it was this guy, we would have to multiply by n. But in this case, we didn't. So if you don't know the theory, don't worry about it. We didn't have to do that extra horrible condition. That's why it makes it worse when you, non-homogeneous and kth order recurrence relations are not easy to solve, it turns out. Also extremely useful in computer sciences. What does that mean now, though? I have to put this into here, into the non-homogeneous, and what does that give me? But b is just a number. So what's t to the n minus 1? Also b. What's t to the n to the 2017? Also b. It's constant. So this says b equals 2b plus 1. One equation, one unknown. Solve that in linear algebra. Oh, I was hoping it would be a negative 1. 2 to the n minus 1 is what I need. Now that says Tn particular is equal to -1. Now let's put that together, and now we use the initial conditions to find the A from the homogeneous part. This first order non-homogeneous recursion relation with initial conditions T1 equals 1 now has solution. Tn equals Tn homogeneous plus Tn particular, which is equal to A times 2 to the n plus -1. T1 equals 1, which equals A times 2 to the 1 minus 1, which says that 2 equals 2 times A, or A equals 1. And this says that the Tower of Hanoi has, well, n rings has the minimum number of moves being a Mersenne number 2 to the n minus 1, for n greater than or equal to 1. Now we have a closed form. Again, what does that do for us? The closed form does this. The open form means that we didn't have, every time I want to know, if I want to know what T7 is, remember I have to compute T6, and then I have to compute T5, and then I don't already want to write that out anymore, the scenario. You saw me do it once, I'm not doing it again. I don't have to. The magic is now we have a, how did you get from here to here? I use two clever ways, but either way, and how will it work for every n? This way we're going to prove it by induction anyway. It always works way out at infinity because we can prove it. Why would I want this? Because now if I want T7, this is 2 to the 7 minus 1, which is 128 minus 1, which is 127. That makes it a whole lot easier. I didn't have to, yeah, this is why we want closed forms. This is why they're doing this to you in whatever class you're taking. They're like, okay, now we're going to do recurrence relations or induction. Yeah, they need to make sure that they have a formula that works so that they can compute it efficiently, and they want to make sure that it actually, the formula actually works for every n, because you can get ones, look at Fermat numbers. He claimed that if n was, yeah, that these were all primes. No, it works for the first few, but careful. We have now a nice closed form for this. I know how to compute, but mathematicians, you're like, yay, finally he can stop talking. Almost. The last thing that we worry about as mathematicians is n. We're saying this works for every n all the way up to infinity, but how do you know that there isn't some number out there which is extremely large and is just going to ruin it? It doesn't work for that. That it seemed to work out for cleverly, but for every n, how can we check? We're finite creatures, we can never actually check all of the integers n. We claim it works for every n. So now again, watch videos on mathematical induction if you want to see this, but what we're going to do is prove by weak mathematical induction that this formula works for every n. If you don't know what we're doing, this is the structure of how correct mathematical induction, including I'll put the sentence at the end mark, that you should wind it up and say, therefore by mathematical induction this statement is true for every n. Yeah, okay, I'll do it because I'm on camera. Here's how it goes. T to the n equals 2 to the n minus 1 for all n greater than or equal to 1. Base step. We're climbing the stairway to heaven now. And then, so there's a base step. Step 1, you have to get on to the step. And then what it's going to say is, as long as you can get onto the nth step, you can also get onto the n plus 1 step. That means you can climb all the way up as high as you want. I don't like this. I like the dominoes falling analogy much better, but we'll do that in the actual videos. We'll see Stairway to Heaven, or why is it always Stairway to Heaven? Maybe you started here on Earth, and then you had to say, oh, damn, I don't want, doesn't matter, get down there. Which way's down when you're on a sphere in 3 dimensions? Alright, good question. So, base step for n equals 1. We know that, we claim that t to the n will be t to the 1, which is 2 to the 1 minus 1, which is 2 minus 1, which is 1. And we have that t1 is 1. So that checks. Good. If you don't like that, start with n equals 2, really, if you want. Okay, well, it won't work for all of them. But t2, we claim, is 2 to the 2 minus 1, which was 4 minus 1, which is 3, and even using our recurrence relation, we found that t2 had to be 2 times t1 plus 1, which is 2 times 1 plus 1, which is 3. Check, it worked. So it's working for them. It worked for n equals 1 and n equals 2. You have to make sure it works for at least one guy's starting point. Then what do? The inductive hypothesis, or the inductive step. I have to say the inductive step. If you can get on the nth step, you can get onto n plus 1 step, down. Or in dominoes, if the nth domino falls, it has to be close enough in space that the n plus 1 domino falls. That means that they're all close enough, they'll all fall in space, and then it doesn't matter how many freaking dominoes you have. It's like, oh no, Kitty walks in and, what are you doing? Oh, I was doing dominoes! And then halfway through setting it up, it goes, yeah, they're all close together, so gone. You should look at YouTube videos on, trying to set up when domino setting up goes wrong, and just a gym full of dominoes, gone. You wasted your weekend. Looked like I speak of the devil. I know we were talking about, can you come in here and mess everything up? Sounds like this one's Noodles or Anubis, right? But we found out Anubis was the Egyptian name for the dog, not the cat. But he does howl like a dog, and you can see that in the other video. So go mess up stuff. Home stretch, inductive hypothesis, kitty break. You need to take small kitty breaks. When a cat comes and wants to snuggle, you do it. Lesson of the day, if you took anything from the video, snuggle a cat when possible. Screw recursion relations and stuff. Snuggle cats when possible. The inductive hypothesis, I'm going to assume that Tn, for n it works, is actually equal to t to the n minus 1. For some n larger than or equal to 1. I need to show Tn plus 1 equals, I put n plus 1 where n is, t to the n plus 1 minus 1. I'm going to show it. And then just to make sure, I put question marks there. That in my mind means when I wrote that down on the page, it didn't imply what you're trying to make it happen always, but it didn't imply that I was just trying to say it's now true. I'm saying I don't know if it's true. So I put question marks there. I'm not saying therefore it is. I need to show this. So when you're doing this, if you don't know where you're going, how are you going to get to the end of it? This is the first part of induction. You always assume an n case, and then you have to look at an n plus 1 case. So you have to look at putting n plus 1 wherever the n is in the original statement. Now I want this to be true, so now I know how to find this. And the other thing I know in recursion relations is we have the definition of the recurrence relation. We know this is true also, which makes it really nice and easy for these types of induction proofs. So I'm going to assume this is true, and I want to show this is true, Tn plus 1. Well, that's going to be fairly easy now, because what I do is, to talk about the n plus 1 case, I can use the recurrence relation to get to here, and then I can talk about the inductive hypothesis and use what I have. I'm about to do it right now. Indeed. T to the n plus 1 equals, by the recurrence relation, this is equal to 2 times Tn plus 1. Why did I do that move? Because now I've assumed something about the inductive hypothesis. I know something about him. He's at 2n minus 1, and I can put that in there. No, he's now 2 to the n minus 1 plus 1. And then FOIL everything out. That gives me 2 times 2 to the n minus 2 plus 1, which is exponent laws, 2 to the n plus 1 minus 1. What that shows is, because I have the recurrence relation also, if I assume that the Tn formula works, the Tn plus 1 formula works, therefore by mathematical induction, the Tn plus 1, what did I do again? In the clever moves, I put in the recursion relations, or recurrence relation, to get a Tn. Now I can talk about the inductive step. Then in there I plug it in. Usually we say by the IH, that was the move that I just used. By the inductive hypothesis, I can put that in there now. I simplify, and I get the formula that I wanted. In a lot of cases, in induction, you have to use a clever trick and some algebra and stuff all along the way. But that's the general idea, especially for recurrence relations. Therefore, by mathematical induction, Tn is equal to 2 to the n minus 1 for every n. Please subscribe. You'll get links to these videos and many more. You can follow us on Facebook at Adrian the Tutor, or on Twitter at the Tutor_Inc. I'll see you next time.